Hi, in this video I will present Carnot groups. Carnot groups are very special metric spaces, in which the distance is Karnaugh and therefore they are geodesic metric spaces. They also have the structure of Lie groups, and moreover they admit dilations, namely maps that dilate the distance by a fixed given factor. Okay, let's see the theory of Carnot groups. If you never saw the definition of a Carnot group, giving the standard definition of Carnot group might scare you a little bit. That's why I don't want to give you immediately the definition. Instead, I want to present the notion of Carnot groups as some object that satisfy axiomatically some very basic properties, and then tell you that actually these objects, they have much more structure. Okay, so I will give you the axiomatic definition of Carnot groups. Okay. So first, a terminology we'll discuss later. Up to the choice of a norm, each Carnot group is equipped with a distance called Karnaugh theory. So, in other words, you still don't know yet what's a Carnot group, but you should think that a Carnot group is some particular metric space. Okay, here's the theorem. Carnot groups, as said, equipped with Karnaugh theory called CC distances, are exactly the metric spaces that have this following 4 properties. So, first property, they are locally compact. They are isometrically homogeneous. I'm going to explain all these terms. They are geodesic spaces and admit at least one dilation, one non-trivial dilation. Okay, you might not have understood anything from this theorem because maybe you don't know any of these terms, but what you have to understand immediately is this fact that this object that we would like to study are metric spaces that satisfy 4 pretty simple to state properties. Okay? So there are 4 properties that are basic, very basic properties for metric spaces. And as soon as you ask for all 4 of them, then you have the object that we will call Carnot groups. This will tell you that Carnot groups are also very natural to appear in mathematics, because as soon as you have these 4 properties, then you're actually and have the presence of Carnot group. Okay, so the metric space with these 4 properties are Carnot groups, and vice versa. Each Carnot group has these 4 properties. Okay, let's discuss these 4 properties because they're very simple, and I can let's clarify what are the properties. So suppose you have a metric space, set with a distance, then this is locally compact. This is the same of saying for all x in X, there exists a compact neighborhood of x in X. Okay. Locally compact. Geodesic. When is it that is a metric space is geodesic? When for every 2 points there exists a curve whose length is exactly the distances. But you can express it directly without talking about length, saying that for any 2 points in the space there exists a number t, which is actually the distance of the 2 points, and there exists a curve from 0t into X that is distance preserving, with gamma of 0 equal X and gamma of t equal Y. So every 2 points in this interval go to 2 points with exactly the same distance in X. This is a geodesic space. Now, what about admitting dilations? Okay, what is a dilation? The dilation is given by a factor, so there exists some lambda. Let's take it larger than 1. And dilation is a map from X into X that is surjective. And has the property that for all x and y in X, the distance of the image points by G is exactly lambda times the distance from X and Y. So we will say that G is a dilation of factor lambda. Okay? For example, the identity map is a dilation of factor lambda equal to 1, but that's why we don't want lambda equal to 1, at least. Okay? And being surjective, of course, the inverse is going to be a dilation of factor 1 over lambda. Okay? So you can dilate the space, so you can find a map that stretches the distance exactly by lambda. This is what a dilation is. And the last point was isometric homogeneity. So a space is isometrically homogeneous if whenever you take 2 points, x and y in X, then you can find a map f from X to X bijection that is distance preserving. So distance preserving distance preserving bijection, so it's also surjective, such that sends f of x sends x to y. Now, terminology, a distance preserving bijection is what is called, by definition, an isometry. Okay? So for every 2 points, we have an isometry that sends the first point to the second point. Good. These are the four properties that will define a Karnaugh group. Okay. Now, going back to isometric homogeneity, what is the main example for having something that is homogeneous is when you are in the presence of a group. Okay. So let me try. The main example of something that is isometric homogeneous is a group. Okay, let's revise why. Okay, so suppose you have a group. Then we say that a distance function, let's call it d on G, is left invariant left invariant if whenever you take 2 points and you translate them by multiplying on the left by an element, then you get the same distance. Okay, this is for all x, y, g elements of the group. Now, okay, so we have we are considering left translations. So the map that to x associate gx, this is called left translation by g. Okay, so these maps are isometries. Moreover, notice that via left translations, you can send any point to any other points. In fact, the map that to every x associate the left translation by y0 x0 minus 1, so y0 x0 minus 1 x as a function in x, this is an isometry if you have a left invariant distance that's mapping a given point x0 to y0. And therefore, if you have a group with a left invariant distance, then this metric space is isometrically homogeneous. Okay, let's continue the discussion on groups. Okay, so let's say that, let's assume we have G a group, but also it's a manifold, and of course in a manifold compatible with a structure compatible with the product law, so on which the structure, group structure, product structure, so multiplication and inverse is smooth as a map between manifolds. So this object here it's called a Lie group. Then let's also assume we are in the presence of a left invariant distance. Left invariant distance. And also assume to have a dilation from G to G, dilation of factor lambda, lambda different than 1. And because of left invariance, it's also we can assume that this lambda fixes the identity element of the group. Suppose we have this setting. Now I will assume something now much stronger, which a priori one consider as a strong assumption, but actually a posteriori this will be always true in Karnaugh groups. I'm going to assume that delta is also a group morphism, group homomorphism. Now, if you're in this setting, then the map delta behaves well on the space of left invariant vector fields on G. So, in this setting, what we have that delta induces a map called delta star on the space of left invariant vector fields. So the space of left invariant vector fields by definitions is called the Lie algebra. of the vector field, of the vector of the Lie group G. This map is in particular a map that is linear. So this star is a linear map that commutes with the bracket of vector fields. Commuting with brackets of vector fields. In other words, this is a Lie algebra automorphism. Okay, let's think of how this map can be done. Okay, let's make it simple for us to understand. So let's assume this for simplicity, that the map on level of vector fields, delta star, is actually a diagonal map. So it means that delta star is going to be lambda 1, lambda 2, lambda n, 0, 0. This is the map in some basis, okay? Let's even make it simple that lambda 1 is less than lambda 2, and so on. Lambda. So this is the map, okay? Now, the fact that delta is a group homomorphism will imply that delta star is a Lie algebra homomorphism. In other words, delta star of the bracket of two vector fields is equal the bracket of the push forward vector fields. So this is bracket of vector fields. Now, let's try to understand what is happening to the standard basis, or namely the vectors that are eigenvalues, that are eigenvectors, which is for this map. Okay, what will make you notice that if so let's say delta star of x, let's say that this is ax, and delta star of y is equal to by, then what happened to delta x of xy? So this is because of this formula here. This is ax comma by, and therefore this is a times b x y. Therefore, you see also the bracket of between x and y is an eigenvector of delta star. Okay, and the eigenvalue has changed. Now it's the product of a and b. Now think that so these are going to be positive values. So now see, if a and b are number, then positive numbers, the a times b, let's say that they are greater than 1, then a times b is greater, strictly greater than a and then to b. Therefore, it means that if you take two eigenvectors or two eigenvalues and take the eigenvector associated, the bracket is going to be next in line. So let me write it as a formula, this statement that I did. So what we have is that if you take the eigenspace of elements with eigenvectors greater than a, and the eigenspace of eigenvector greater than b, or eigenvalue greater than b, then the bracket is going to be greater than a b. Okay, so this is the eigenspace of eigenvalue greater than or equal to a.
Since the initial map delta is a dilation, we may assume that the eigenvalues have norm greater than 1.
This observation makes you prove that if you take iterated bracket, then since every time the eigenvector changes, then eventually you should have 0. So this implies that the Lie algebra G is nilpotent. This means that if you perform the bracket enough times, then this is just the 0 vector, the only vector that can be, there's an eigenvector for any eigenvalue. Actually, more is true because of this formula here. One can prove that not only this property here, but also you can prove that G is what's said positively graded. Namely, you can write G as the sum of subspaces Ts such that, okay, every Tj is greater than 0, and the bracket between Vt and Vtj, Ti and Tj, this is inside Vti plus Tj. So what are actually these vector space? This should be the eigens, by definition, the eigenspaces of eigenvalue. So since I want to make it additive instead of multiplicative, I should take the logarithm log of t. No, I should do e to the ti exp of t1. Okay. Now, this was just to make you understand that something stronger should be true for Lie groups that admit dilations that are automorphisms. And I kind of gave you the proof of the theorem, at least in some special case. Everything can be really proved in a more general setting, and this goes as a theorem due to Siebert. And this is the theorem. So if a Lie group admits an expanding automorphism, then it is nilpotent, contractible. Okay, the fact that it's contractible is clear. Contractible. And its Lie algebra is positively graded. Okay, so this is a theorem. Okay. Now at this moment, we can give the definition of Karnaugh groups from the algebraic point of view. And so I'll go back for the definition, but from this point of view of positively graded Lie algebra, I can go ahead and give you the definition of Karnaugh groups. So Karnaugh groups are those contractible or simply connected for nilpotent groups is the same, contractible Lie group, G with Lie algebras G that is positively graded. So G has a sum t greater than 0 Vt with an extra property, and such that V1 generates, namely the layer of this is called grading. The space of degree 1 is not contained in any subalgebra of G. So the Lie algebra generated by V1 is anything. I will now rephrase the definition of Carnot group. I will actually first define a Carnot algebra and then a Carnot group. Okay, so definition of Carnot algebra. Carnot algebra. So a Lie algebra G is called a Carnot algebra if it is equipped with a direct sum decomposition let's write G equal V1 Vs such that V1 bracket Vj is equal to Vj plus 1.
Where with j equal to s, it means that Vs commutes with V1.
So a little bit of observation. Okay, not all the algebra can be equipped with such a direct sum. Okay, so one should say a Carnot algebra is a Lie algebra for which there exists one such decomposition, and we have fixed one such decomposition. Okay, so this decomposition here, as a terminology, this is called stratification. Okay, so let's make some remarks. So first, we okay, not all Lie algebras are stratifiable. In the sense, admit some stratification. Okay. 2, we really require equality here, equal, because you see, if you only have containment, then this would just be a weaker requirement than asking positively graded. Okay, I mean, otherwise every positively graded would do it. However, it's even true that not all positively graded Lie algebras admit stratifications. Okay? But still, right, from this property, you can prove that also you have Vi bracket Vj is equal to Vi plus j. So as a consequence, we really have positively graded you have vi, vj is contained vi plus j. So we have that it is positively graded and therefore nilpotent. Okay, good. Okay, now we have given a name to this, the algebra that admit a stratification. We call them Carnot algebras. Okay. Now let's remember that whenever you have a Lie algebra, you have always one simply connected Lie group with that Lie algebra. Okay, it's the fact that for every Lie algebra, fact that it has to be finite dimensional and over R. Then there exists actually unique up to isomorphism, a simply connected Lie group with the algebra. So let's give a name to the algebra here, G. Now with this Lie algebra G equal to the Lie algebra of the group G, and equal to the left invariant vector fields on G. The Lie algebra. Okay, now keeping this in mind, what is finally a Karnaugh group? A simply connected Karnaugh group, Lie group G, such that its Lie algebra, space of left invariant vector field on G, is a Carnot algebra, is called Karnaugh group. So again, Karnaugh groups are those simply connected Karnaugh groups whose Lie algebra, whose space of left invariant vector fields, admits a stratification. Okay. Now we will need to see now what are the properties of the presence of this stratification. I will remark a fact about stratifications on stratifiable Lie algebras. Right? So a Carnot algebra is a Lie algebra that admits a stratification and on which we have fixed one. Of course, the natural question is, okay, in how many ways we can stratify a Lie algebra? And quickly, the answer is in just one way. Okay, so let's this fact. Don't know if I will prove it. Maybe I will link to another video. So if you have V1, Vs, and W1, Wt, a priori might be a different step. S might be different than T. Let's suppose that these are two stratifications of the same stratifiable Lie algebra. Then
S is equal to T and
there exists a Lie group, a Lie algebra isomorphism. Let's call it phi from G to G. So it's an automorphism, yeah, such that the map phi sends the ith layer respect to V to the ith layer respect to W for all in degrees I. So in other words, what we've said that if a Lie algebra is stratifiable, then its stratification is unique up to automorphism. If you like the video, you can let me know by clicking the like button. This will also suggest the course to other people. If you want to see more videos on subRiemannian geometry, please subscribe to the channel clicking below. Bye.